Hello, everybody. My name is Ali Kujuri. I was expecting more students and so on, but it seems that they are busy. For today, we have Dr. Rajiv Dighe, who is coming from Broadcom to give us a lecture on fiber to the home, and it's in fact called the fiber, the X-year fiber to the home, or let's say to the neighborhood and so on, and which is in fact using the passive optical network. Before I introduce him, let me mention that next 2 weeks from now, we have another interesting talk by Dr. Sarah Cases, and the title of her talk is Material Characterization Techniques using the Keck Macroanalysis Laboratory. Okay, Dr. Rajiv Dighe got his PhD in electrical engineering from University of Notre Dame in Indiana in 1986. He has started his career at AT&T Bell Labs working on broadband networks. He is a broadband systems architect with more than 30 years experience in architecting and building packet-based platforms for next generation networks, as well as digital subscriber loops and passive optical networks chipsets. He holds 22 US patents and currently manages the EPON based home gateway system on chips for Broadcom. So here is Dr. Dighe.
Thank you. Today I'll talk about fiber to the X, X being home, basement, curb, you name it. And we'll focus mostly on, I'll talk a little bit about the PON technology, and then I'll talk about market and trends, where this technology is going, and I'll go pretty much region by region, talking to you about what's happening where. Very interactive. Stop me whenever you want, and you can ask questions. So, broadband market drivers. What's driving this broadband frenzy is a question mark. And before I get into that, let's just define what I call as broadband fixed access. So you basically have essentially all the different customer premise solutions. There's a residential service, there's a multi-dwelling unit, business services, mobile backhaul. And all of this is fed into what I call as an access network. And the access network can be a coax-based network, which will have a CMTS, like a cable solution, or a DSL-based network, which will have an IPD-SLAM. So this is something what Comcast would do. This is something what AT&T UVerse would do. Or a fiber solution where you bring, which is what Verizon's doing, or point-to-point Ethernet. So this is basically what I call as an access network or the last mile network. And then, of course, it feeds into the core network, which will typically have MPLS ring, followed by the big DWDM routers and things like that. So today I'll spend my time talking about this particular network. So the key here is to bring broadband to the network, or to the home, and can be done with DSL, cable, or fiber, basically the three. And then you need to deliver the medium into the home. And the technology you can use is like Ethernet, or MoCA, which is over coax, or the home plug, which is over power line, or Wi-Fi, right? And so the basic idea here is deliver bandwidth to the home and then distribute it using these home networking technologies. And what's making this thing very interesting going forward is that the number of these devices is just growing exponentially. I mean, when you look at it from a business sense, I can sell one modem per home, right? But I can easily see myself selling 20, 30 of these devices inside the home. So the TAM just grows super linearly, and that's where the whole Internet of Things gets into play. And one critical piece of that whole Internet of Things here is the home gateway, this broadband router, because that basically controls how these devices connect, how they talk to each other, and all of that. So this piece here, I think, is the hub that's going to make the Internet of Things happen. So I forgot a few more home networking technologies. So Bluetooth is obviously there, and then DLNA is the software that runs on it. So what is driving this? And you can see the problem here. The problem is the revenues are flat, and the traffic's growing, right? So you can see that this will always be a good analogy that somebody made in the early broadband days, and they were saying that the carriers have got it all wrong. The carriers are sort of literally making you pay per bit. So if you 10 megabit service, you pay so much. 100 megabit service, you pay so much. 1 gigabit service, you pay so much. The mindset is wrong. They should treat it like the power company. The power company gives you a connection, and they try to put as much current in there as possible, and then make money on the usage of that thing. So they're basically saying that instead of metering tightly how we bring the bandwidth in, we need to just bring bandwidth to the home, and then find solutions that will use it up. And I think Google is exactly in that mode right now. They're just driving that whole thing. So here's the problem. The traffic is just growing, and this is costing money. I mean, you're putting stuff down to meet this traffic need, but the revenue is just flat. So you need to start thinking of new things to do. You need to go to triple play. You need to go to 3D TV, Wi-Fi backhaul, surveillance, business services, cloud computing. You need to keep adding more and more services like that.
By data traffic, do you mean about users using the internet, or?
Yeah, I mean, basic.
Data being pushed?
Right. So the basic idea is you need to start charging for services here, and that's what's driving it. Because if you just stayed with voice plus basic internet data, you're not going to monetize it in a very effective way. So services is what's actually going to be driving, and these are all these new broadband services. So a lot of these fiber-based technologies will coexist, depending on the, it's interesting. This is called local access because it's truly local. Every access, every neighborhood, the technology of delivering the bandwidth to the home will change. And there is no one answer for everything. So another thing that's happening is currently you see two very different networks. You've got a mobile network and a fixed network. If you look at a Verizon or an AT&T or so these are two distinct networks, and that's expensive, right? So you need to collapse that into one single network, and that's the converged network that I'm talking about, where it's all fiber. A lot of it is fiber fed, and you run services on top of that. So the cellular services are also sitting on top of the same network. The fixed services are also sitting on top of the same network. So the idea is to combine these two very expensive networks into one converged network, and that's the vision. And on that one converged network, you can start providing triple play services, 3G, 4G, 5G networks with 1588, clock transport, and high-speed business services. So I think this is the model, and this is what's driving the growth of broadband worldwide. So very quickly I'll go over what PON is. So you've seen this. This is point-to-point Ethernet. So there's one fiber that runs from the central office to each home. And it's a dedicated port. And the CO tends to be port constrained. You can't have millions of ports if you have millions of subscribers. So this leads to this, what is called as fiber exhaust or a conduit exhaust, and managing this now becomes a problem. Okay, so this is the most basic fiber network. It's a point-to-point network. You can do a little bit better than that. You can take one fiber to a switch in the field and then start running that off. So that's like a remote solution. But it will need power inside, in the middle of the network, and that's not attractive. Right? In countries like USA, that's a problem. In some other countries, like where I came from in India, a lot of this stuff would just get stolen. Right? So that used to be an issue. Right? So this has its limitations. So the way they have solved this problem is with a passive optical network. So you have a CO, and you have the CPE. And on the CO, you have what is called as an OLT, optical line terminal. And then on the CPE, you got an ONU. And the beauty is the network in the middle is passive. So it's just basically fiber that's connected with a splitter. And the splitter is a power splitter. So, there's a 3 dB drop across every split. And they can do now things like you can put 32 users on one fiber, you can go to 64 users, you can go to 128 users, and that's a rate reach kind of a thing you do. So this is the basic network. It is a distributed switch in a way because essentially these two, there's a very tight coupling between these two, okay? Now the way you work the protocol is simple. You say on the downstream I'm going to go broadcast, so everything goes to everybody in the downstream direction. Inside each of these CPEs, or what is called as ONU, they have the ability to filter out data that does not belong to them. Then on the upstream, you have something called TDMA, so time division multiple access. And basically, the CO is the one that allocates to grants. So he's saying, you go first, you go next, you go next, you go next, you go next, and it works that way. In order for this guy to get a little bit more intelligent with the way he does things, these guys will send queue reports saying, hey, I got this much traffic, and it even gets more sophisticated. You can say, I got this much traffic of this traffic class. So I have so many data packets, I have so many voice packets, I have so many video packets. And then this guy can now create an algorithm which is called dynamic bandwidth allocation that will streamline this. Okay. So again, PON is a distributed switch. The central scheduler is in the OLT, and the OLT and the ONU employ a number of protocols to act as one device. As I said, downstream broadcast, upstream TDMA. Very simple solution. Very elegant because the whole the whole ODN or the optical network is passive. There is no electrical inside in the middle of the field at all. It's all end-to-end. Has another nice property that if you look at a point-to-point solution, if you have N ports talking to N CPE devices, you need two N electrical terminator or electronic terminators, basically. One on the OLT side, N on this side and N on this side. Now in the case of PON, because of the point to multipoint, you need just one here and N here. So your complexity goes from a 2N complexity to N plus 1. Again, so very simply, you have a CO, you have the CPE, It's a point-to-multipoint solution with downstream broadcast and upstream TDMA. The OLT gives upstream grants to ONUs. And the grant is basically a size of the grant in bytes and a time to transmit. So it's saying, transmit this much at this time. The time is a critical element because note that these are all locally disparate, right? They are, one may be far, one may be near, within a 20 kilometer or 10 kilometer. So there is a propagation delay that's different across these different ONUs. Now, one of the first things we do in the registration and the discovery protocol is we figure that out, and the OLT actually does take the propagation delay of each OLT into account when it's doing its granting. So it's almost like a pipeline scheduler, if you will. Yeah.
So is that important on the receiving end, the delay, to make sure everything?
Yeah, you want to make sure, because of the TDMA, effectively this whole network is time synced in the upstream direction. So there are slots, and you want to make sure that each ONU is sending at the slot it's supposed to send, and you're not wasting slots, because if you waste slots, that's wasting bandwidth. So view it as a super scheduler in a network that's inherently not time synced, but then you've added protocols to time sync it essentially. So you can see that OLT and the ONUs have a time sync to make grants meaningful, and the delay between the two is calculated during the discovery phase of the PON protocol. Anytime a new ONU comes in, it has to register, and the OLT responds back to the ONU with an ONU ID. The ONU ID is a very critical factor because in the downstream broadcast, you use that ONU ID to see if stuff is for you or it's not for you. You can filter things out. So this is the basic system that we are deploying. Again, the upstream TDMA is interesting. It's based on a demand and grant, so each ONU says, I need so much of this traffic type, and then the OLT sends a schedule. The brains of the ONU is in the DBA. The goal of the DBA is to maximize efficiency on the link, but also provide fairness and be QoS aware. So if you have different traffic classes, you need to make sure that you give grants based on what the SLA is. So for instance, typically you can sign up, they have different ways of trawling it, but you may have a bronze service, you may have a silver service, and you may have a gold service or a platinum service, and you pay $40 for a bronze service, so on and so forth. This is typical with all the SLAs you sign with the Verizon or AT&T or a Comcast. And you need to ensure, because of that the guy who's paying $100 gets the quality of service that he's paying for, as opposed to the guy who pays $40. So there are two aspects to it. On the upstream, it's this DBA. On the downstream, it's metering. You have to actually do the switch inside the OLT actually has to do what is called a fine-grained metering, and that's SLA aware. And the SLA is a higher level construct. So you basically break it up into multiple queues with and a scheduler, a static priority or a dynamic weighted round robin or a weighted round robin scheduler. And that actually maps to what the SLA was when you signed it. There are two ways to do it. There are two standards, unfortunately, and I'll talk a little bit about that. EPON uses something called a LLID, and GPON uses something called TCONs. And TCON is a traffic container, LLID is a logical link ID, and they're both used essentially for the same purpose, which is reporting queues on a per class basis, and then giving grants on a per class basis that each of the ONU can adhere to. Now, this is a nice goal, and Ryan here will tell you that it's not easy to realize, where ideally you would want to grant on a per application basis, not just the ONU, but maybe a set-top box sitting on top of an ONU, maybe a video service sitting on the set-top box. So ideally, the ideal scheduler would grant on a per application basis. But the problem that happens with that is the state explodes, right? There's only so much state you can manage at the PON level. So you need to start putting things into a container and trying to do it on a traffic class basis. Okay, this is where it gets controversial. There are two PONs. One is Ethernet EPON, and that was standardized by 802.3. I think a pioneering company for EPON came straight out of Petaluma. It was Technovus. Ryan was one of the original contributor to that standard. And actually, Dr. Kramer must have come here. He was the chairman of this. And EPON was based on a very simple concept. There's only one world in the world, and it's Ethernet. There's nothing else. Okay? And it's kind of ironic for me and Dr. Ali, because he was doing the ATM forum, and we went through the same debate back in the 80s. In fact, I had a series of patents on a protocol that we thought should have been ATM, which was called quantum packet mode, and it was based on it was a variable length thing, but it was just based on quantums. So instead of down to the last byte, we were down to the last 8 bytes or whatever. It was a function of the way that switch was designed. And it was all based on the fact that the world is finally going to be variable length, and the cell business that ATM was doing was an artificial construct. And unfortunately, the telco world had a vision of the world, and in that vision they had 3 different traffic types. They had packets or data, they had TDM, which was circuit switch, which is where they started from, and then they had a third type, which was a mixed mode. We would call it video or real-time video. So they basically said that in our world we will have these 3 types, and we need to find a way to sort of differentiate one from the other. And our world lives and dies by the 125 microsecond world. This came from the SOUNET days, it came from the T1 world. And so they built a system called GPON now. Used to be ATM, also had the same issues. And it was basically an encapsulation, and everything is on a 125 microsecond boundary. These guys says, no, the world is all Ethernet and IP, and circuit switch traffic is all going to ride on top of Ethernet and IP, and I don't need anything else. And EPON is just based on that. It's just pure packets. While these guys have frame fragmentation, and there's an overhead associated with it, because you now need to take a packet, you break it up into chunks, and you put a header on top of the chunk, and send it out. So that's the main difference between GPON and EPON. So this is what that whole gem layer is called. It's called GPON encapsulation method. And then the rate they picked was, they could go 1 gig, 1.5, 2.4, 10. This is an older one, but I think it's mostly 2.5 down and 1 up. And upstream was 1, and they would use scrambling for the line coding. On the other hand, the EPON guys, and IEEE used to be pretty religious about it. Their rates were always a function of 10. So it was 10 megabits, 100 megabits, 1 gigabit, 10 gigabit. They didn't do any of these 2.4 and 2.5 things. So they went with downstream of 1 and upstream of 1. And then the next standard they did was 1010, which is the 10 gig EPON. And for the line coding, they use 8B, 10B at 1 gig and 64B, 66B for the 10 gig. So 2 different standards, 2 different bodies. Now some characteristics of PON. capacity sharing is a crucial advantage of PON. In a point-to-point solution, you can often waste a lot of capacity if the traffic is bursty, or there's a lot of idle periods when you're not using anything. In a PON system, because of the aggregation and the point-to-multipoint nature, you can actually take advantage of the burstiness of the traffic, and so if one is not transmitting, somebody else is transmitting, you can actually move the resources around in a very flexible ways. And an interesting discovery was done in I think it was in the late 80s, where we've always lived in a world of Poisson traffic, and all our initial queuing models, everything was based on the MM1 system and Poisson traffic and central limit theorem. We used all of that. And it was a rude shock when we first did the first set of switches we built in the mid-80s, that as soon as you came from a circuit switch network, a circuit switch network is inherently constrained. So you got these 64 kilobit chunks that become 1.536 megabits that go on to 45 megabits. And we were doing this frame relay network, remember. And that network was a flat network. The access line speed was the same as the core network speed. And all these traffic models we were doing just fell on the face because there was nothing Poisson about it. There was nothing, So we went back and checked, and we also lived with very small buffers those days because that was hard. So we found out that it is self-similar, actually. If you look at the internet traffic, it's fractal in the sense that if you take any time constant, the shape looks the same. And it's bursty. There is no issue about it. So PON is actually beautiful for that because allocating fixed pipe is very inefficient, and PON actually allows you to instantaneously distribute capacity. And that's what the DBA does, right? I mean, suddenly something gets filled up, you send a queue length report, and immediately the OLT can give you a grant. So that's attractive. The other thing is, even for point-to-point Ethernet networks, we can see that EPON with 10 gigabit aggregated as compared to point-to-point 1 gig solutions, this is a better solution. So we're seeing this result in two things. PON is being actively used for all broadband networks, to the home, to the basement, to this thing, but it's also now being used as a backhaul for cell traffic. So it's actually becoming very popular. It's also green. Why is it green? It's green because there is no electronics in the field. It's all passive, right? So the electronics are only at the edges, and we have techniques where we can shut down the entire laser if there's nothing to transmit, and we only turn it on when there's something to transmit. So essentially, it's actually a very it's a very power efficient method, and it's essentially green. And that's why fiber to the home is actually the greenest, because now from the home to the central office, everything is passive. The only optics, the only electronics are in the home and the central office. You don't need to do things like battery backup and the standard stuff that we used to wrestle around with in the telco world for a very long time. Okay, so this is where things get complicated. We just have too many PONs. In fact, actually, Dr. Kramer had an interesting talk where how many PONs, and it was based on Dr. Seuss's, and it was really interesting, because I think the problem is that the more standards you create, the more resources the technology companies have to spend to build these standards. And you're basically, essentially, fragmenting a market that doesn't need to be fragmented. So I think that's one of the problems. But just for this thing, the first ATM PON that came out was also called BPON. It was based on 983 ATM cells, 622 down, 155 up. Standard in 1998. GPON came about, ITU G.984, same time as EPON. So GPON was 2.5 down, 1.24 up. Carries TDM, ATM, and Ethernet frames, and was standard in 2003. Same time, EPON came about, used to use Ethernet, 1 gig symmetric in 2004. And then there was a turbo EPON that we did, which was, again, Techno was driving that. It was 2 down, 1 up. And that was standardized in 2009. Going forward, people have started working on the 10 gig space. There's an XGPON 1, 987, XGPON 2. I think now it's 989, right? This slide is a little old, but I think it has a number now, if I'm not mistaken. And then NGPON 2, which is
I think that's actually
wavelength division multiplexing solution where you have 4 lambdas. And on the IEEE side, you started with EPON, turbo EPON, 10 gig EPON, and now coming up is the next gen EPON, which is basically a 25 gig solution that can go up to 100 gig by taking 4 lambdas. So things are moving, the bandwidth is going up, and there's a lot of work going on in defining these standards. So again, GPON, EPON, 2.5 down, 1.25 up, has a cable TV support, 1 gig symmetric, also has cable TV support. And the basic difference, as I said, GPON was designed to work with ATM, TDM, and Ethernet, while EPON was basically worked with Ethernet. In the end, almost all the circuit switch traffic is now carried as IP in packets. In a way, some of these encapsulation was not needed. Again, GPON operates over 125 microsecond frame, and EPON just uses complete Ethernet frames. And then power budgets were different between GPON and EPON: Class A, Class B, Class B+, Class C, C++. EPON initially started with very simple, the PX10, the PX20, and then added the 30 and the 34. Coexistence was another difference between these two. So you notice that in the EPON world, suppose you have 10 gig and 1 gig, and this is very important, right? If you think about it, you've got a PON network. You will have some fiber to the home customers that only need a gigabit. You will have some business customers that do need 10 gig, or you may have an MDU that feeds in further down that may need the 10 gig. You want all of it to sit on the same PON, so coexistence was important. The way EPON did it was that they had one frequency for 1 gig downstream, one frequency for 10 gig downstream, but the upstream was shared. So it was the same TDMA that worked between 1 gig and 10 gig. And that's the beauty, right? Now you can actually do this super scheduler where everything is sitting on the same thing. GPON did it slightly differently. They have a different frequency for downstream, and a different frequency for upstream. So more lambdas. Now, what happens typically? A lot of the cost of this solution is in the optics. So if you go with this, with the lesser number of frequencies you have, it makes the optics cheaper. And in the PON world, the area of interest in terms of cost is the CPE. The CO can actually be a little bit more complicated in terms of the optics, but the CPE needs to have very simple optics. So unfortunately, this puts the onus of the CPE. So it's a little bit of a disadvantage. Okay. So anyway, the goal, as I said, is you got multiple PON standards. Unfortunate, but that's the way the standards have evolved. A CO, and then you can now go fiber to the home, or you can go fiber to carrier Wi-Fi kind of a situation, cell backhaul, or you can do fiber to the distribution point and there go VDSL out, or you can go fiber to the basement and go Dighe out, so there's a LAN over there, or fiber to the basement with DSL out, or fiber to the basement with coax out, or business services. All of it sitting on the same PON network, and I think that's what we would like to see. Because a lot of the savings comes from a universal service platform that sits behind this, right? So you can run all these different services, and then you have, your routers and your service platforms, your ACS servers and things. Also, if you can actually leverage all of that, use a protocol like TR69 from here all the way to the different CPEs. I think that's where the same. Okay, so that was the technology. Now let's talk about the market. It's always good to see what was predicted and how did we do. Okay, so this is a 2009 chart, and in 2009 they were saying that this thing is going to grow. You see the DSL and cable looking pretty flat year over year, but the growth is all in the fiber. Almost 25% CAGR is predicted. And let's pick a number. Right? So 2015 is a good number. And the total 700 million subscribers is what we predicted in 2009 and what 2015 is going to look like. And the prediction was a lot of that growth was going to come from Asia, China, Japan, and see some small increases in Europe and North America. So this is what OVM was predicting back in 2009. How did we do is the question. And this is the 2015 prediction. And you can see that we're close to 700 million. I think it was pretty bang on, actually. I'm actually surprised. And you can see the same growth that you're seeing in fiber compared to the other two. And again, we grew at more than 25%. We were predicting 25%. So I think that 2009 prediction was pretty good. Let's look at some dynamics. 2015 was a bumper year for PON. More than 80 million devices shipped. There was a period of time when Broadcom, was shipping 1 million a week. And the only reason we were being constrained to 1 million a week was because of the optical components were in short supply. The BOSAs and things, it was not our. So huge increase. And the cost keeps going down as the reliability and the performance continues to improve. And now the focus has moved to in-home diagnostics and speed service tests and application identification, more service-centric things that sit in the home. Just as I pointed out, that's where the revenue models are going to come back. So I think we have gone past the initial teething stage of PON. I think it's a very well-established network. We're shipping a lot of it. Focus now on services and software. A lot of the initial PON deployments were two-box models. By a two-box model, you typically see a modem that you can buy, or a Comcast or AT&T or Verizon would send you. And sitting behind the modem is a router that you buy from Best Buy, like a Linksys or Netgear. So that's a traditional two-box model. Now, because of the need to increase their silicon content, all these carriers are integrating that router into the modem. So you're moving from a two-box model to a one-box model. Comcast is a good example, where the first one I got was a simple modem. Now it's got a Wi-Fi integrated. You will see that. So carriers are moving to a single-box model. It leads to cost reductions. And this is an important piece. Owning the gateway is owning the customer. And owning the customer is owning control of all the devices inside the home. And that's the whole IoT play that comes in. You've got that gateway, you've got the software, now you're in control of everything that's in the home. And that's monetization opportunities. And the other big thing that's happening is wireless LAN. Everything is going wireless LAN. I showed you a bunch of technologies, Ethernet, MoCA, all of that. Almost most of the big carriers now think wireless LAN is the way they're going. They're going to run data on wireless LAN, no issue. Now they're running video on wireless LAN. Everybody wants to run over-the-top video on the 5 gigahertz. So this attach rate is improving. We're seeing a demand for interoperability at the PON layer, either with the IEEE OAM or OMCI, because then the carrier can pick and choose who he wants on the CO side and who he wants on the CP side. And that essentially can increase the ecosystem and reduce the cost of the solution. As I've mentioned, there's this standard called NG-PON2. It's got tunable optics. The cost of the tunable optics is becoming a little critical, so there's a new solution coming out which uses the same technique as 10 gig EPON, but it's an ITU standard, it's not an IEEE standard, it's called XGS-PON. We're seeing field trials in 2016. Actually, 10 gig EPON is actually growing. I mean, in fact, 10 gig EPON in China this year will, they're predicting almost 1 million CPUs already. So 10 gig EPON is already taken off in my mind. But the rest of the other ones may start growing in 2017. Again, you're seeing, we believe this 2.5 gig GPON or 1 gig EPON will last for at least another 4 to 5 years. And the next technology cycle, I think, is going to begin in 2018, but we're seeing lab trials at 10 gig. Okay, let's talk about a few regional trends. North America, again, these guys were farsighted enough to know that they didn't really care about being an ISP or a telco, but they did feel the need to have more bandwidth in the home, because if they had more bandwidth in the home, their applications would drive it. So Google got into this game just to drive the applications, the need for bandwidth for all their Android-based applications. Right? But this led to a bandwidth war because they announced 1 gig to the home. Verizon and Comcast were already in that battle. I mean, Verizon was like 300 megabits to the home. Comcast would come back with 305 megabits to the home. But then these guys just came and upped the ante to 1 gig. So obviously everybody had to follow. So AT&T said, okay, our gigapower will also be a gig to the home. And then Comcast sitting and scratching his head and said, okay, we're going to go 2 gig to the home. 2 gig was an interesting number because they announced 2 gig symmetric. So GPON is 2.5 down, 1 up, so that doesn't meet it. And DOCSIS 3.1 is 5 down, 1 up, that doesn't meet it. So the only way Comcast can get to 2 gig symmetric is going 10 gig EPON. And that's what they're doing. And now Verizon's saying, now what am I going to do? So they're looking at NG-PON 2 as a way to up the ante further because they can go 4 lambdas and potentially all the way up to 40 gig to the home. Who else needs 40 gigs to the home? I don't know. But, it's a bandwidth war. So that's happening, which is good for us as technologists. If there's a market, we can keep innovating and coming up with technologies to meet the market needs. So anytime there's a bandwidth war, it's always good for the technologists. So that's happening. The second thing that's happening is not of too much interest here, but carriers are changing their model. So instead of, in the old days, carriers would buy from a vendor like Alcatel or Adtran or Lucent. Now they want to go to a new model where they actually want to own the platform. So they may go to a contract manufacturer to get the hardware done and then put their own software on it. We're seeing this also with this whole open software architecture that people are talking about. So they're looking to basically take charge of that platform and own it. And again, I said, there are lawsuits going on the 5 gigahertz Wi-Fi. I mean, you saw CenturyLink suing Verizon because Verizon claimed they had the highest performing Wi-Fi, and CenturyLink thought they had a better one. So this is now becoming a very critical differentiator. What do you put on your 5 gigahertz Wi-Fi for streaming video? So we started with 3x3 11AC, we moved to 4x4 11AC. People are now talking about 8x8 11AC. And then there's a new standard called 11AX, that's 8.5 gig of Wi-Fi throughput. So this is now becoming a big differentiator. Europe's growing, so you can see Portugal Telecom in Portugal, Brazil, Angola, and Namibia. SFR is shipping in France. Marco Polo is a Telefonica initiative, and they're shipping into Spain, Brazil, and Europe. France Telecom is starting trials, and so is Freebox. So Europe I'm seeing a lot of dynamics in PON. Russia, one of the best defined home gateways came out of Russia, Rostelecom, 4 years ago. It's a very high-end home gateway with GPON and dual band concurrent Wi-Fi. So their goal is to get to 20 million homes in 2020. Now, if you're talking about goals, I think I just want to point out, China had a goal where they said they want to get to 100 megabit to the home by 2015 for 100 million subscribers. So that was the goal, 100 megabits, 100 million subscribers, 2015. They beat that goal by 2 years. By 2013, they'd already reached it. So massive growth in China. I think we're seeing the same in Russia now, and in MGTS, which is in Moscow. The interesting thing about a country like Russia is that it's not very conducive to copper. It's very cold. It's a lot of frozen. Fiber tends to be a better candidate for Russia. Again, Brazil, Telefonica is almost 4 million passed, and I'm seeing trials going on with GVT, NET, Embratel, OE. Again, we're seeing a lot of fiber-based growth coming out of Brazil. And India is an interesting broadband region. I mean, whenever I look at this number, I'm amazed. India's got more than 1 billion smartphone users. But the number of broadband users is greater than 10 million. So you can see there's a huge gap. I mean, there is an absolute, growth opportunities are there because India is just, they use the smartphone for everything, banking, you name it. I mean, it's almost like, every time I go back home, I ask these guys, I said, in the US, if you're a 7th grader and you don't have an internet connection to the home, you're in trouble because so much of your homework is online, right? India is not there yet, but I think it's going to get there. A couple of initiatives that have happened in India are quite interesting. This is called Fiber to the Panchayat. I don't know, do you guys know what a panchayat is? Okay, so in a village, there's a tribunal or a council of wise men, and if there's any problem inside the village, they bring their complaints to the panchayat, which then makes judgment. Okay, so that was the basic of the word panchayat, which basically punch means complaint, so it's a place to, but this basically means fiber to the village. And there was a guy who worked for General Electric back in, I would say, early 80s, late 70s. His name was Sam Pitroda. And he came up with this very interesting concept of, in those days it was all circuit switch networks. He came up with something called racks, which was based on burst switching. So he would actually, inside his switch, this is before the whole packet thing, he would switch from a burst to a burst, and then he would claim that for countries like India, where people didn't talk much, he could sort of, or one guy listened, the other guy talked, he could actually come up with a better efficiency. Anyway, Sam did well in USA and then went to India and basically started this whole fiber movement in India and worked for the government of India as one of the, in one of the commissions as their technology wonk. He came up with a very interesting idea. He basically said that India's got a problem because too many illiterate kids, right, especially in the village, right? And he claimed, and it's something to think about, he claimed that it would be easier for him to teach a kid how to operate a computer and a mouse than teach him the traditional alphabet, And there's something to it, right? I mean, icons are maybe easier to catch and capture. So this whole concept was started by the government of India, where they were basically saying they're going to put fiber into every village, they're going to put Wi-Fi in every village, and they are going to provide notebooks to all the kids in the village. And the basic idea was to improve literacy by improving computer literacy. And so this whole project was started. It was called the Next Generation Optical Fiber Network, and it aimed at creating Wi-Fi connectivity. First tender was 250K ONUs and 50K OLTs. Pretty large, and it's been, I'm happy to say that we are the supplier for that because we've been working for a long time with CDOT, which was their research thing. So both sides are now Broadcom based. But for me, it was a very interesting experience working with that. There's a new company called Reliance that has started, and they are just going gangbusters. I mean, they've already shipped about 500,000, and they're projecting maybe 1 million a quarter coming up. I think they're going to change the dynamics in India, and I'm expecting to see this 10 million number get to more where it should be, like half a billion or so. So how was the market? And you can see that this is Infinetics in 15. It thought we would do around 65 million units in 15. I know for a fact it went over 80. So they're already conservative. A couple of other things. They're showing this going down. I just don't see any way this is going down. In fact, actually, I think this is just going to go up. So maybe 5 years later, I'll come back. We can look at these numbers again. So what are the PON applications? Fiber to the home. This is the biggest application right now. Fiber to the basement, fiber to the curb, fiber to the node, MDU with VDSL or Ethernet. Backhaul, where you can send things over, use the PON to send cell backhaul. Fiber to the distribution point, fiber to a CMCC or coax media, and from there you can go coax, so you come fiber to that box and then go coax to the home or business services. Again, the FTTH has two models. There's a two-box model, so you have a modem and then a home router. And then there's a home gateway where everything is integrated on one box. And we're seeing a definite trend from this model to this model. So you can see the different PON applications from a single family unit to a dual band concurrent home gateway, Ethernet MDUs, VDSL MDUs, G.fast, small cell, CBU, Wi-Fi. One thing that our CTO in Broadcom says that 99.99% of all the traffic in the world will go through at least one Broadcom device. And it's an amazing claim, and it's probably true. We do cover every aspect of the access network, the core network, and the data centers. So this is a bridge, PON in, GIGI out, and you can have multi-port And then this is the most popular one. China is all over this one. This is your concurrent dual band home gateway, 2.4 gig Wi-Fi, 5 gig Wi-Fi. India, by the way, Reliance is also doing that. Our chip is kind of nice. It integrates the gigies, the USB, the voice, and you got the Wi-Fi out there. You can see how much integration is on this chip, because almost everything is, anything that is digital is integrated, leaving just memory and flash, and then leads to a very, very cost-effective solution. And then the different MDU applications, whether you can have Gigi-based MDUs or VDSL or G.fast. And then the cellular backhaul is an important application. Here, one of the advantages of PON is that we are able to recover clock and, with a 1 PPS clock and a time of day from the PON signal. And we can use that to drive the circuit switch network behind it. So you can see this 1 PPS and TOD being fed into a switch, which can then run a 1588 into the cell network. Or a small cell gateway, like these little femto cells. So you have a home gateway with the femto, and then you can essentially switch between the femto network and the WLAN network. Seen a lot of that. And this is the distribution point. This is an interesting application. This is where the MDU, if you will, sits in a trench or a basement, and so there's no power in there, okay? So what you do here is you have PON terminated here, and then you go out DSL to each home, right? Because this box has no power, it needs to reverse power. By reverse power, I mean the CPU in the house has to power this thing. Now you may have 16 to 32 CPEs on this DPU, and 31 out of the 32 may be shut down, may not even be working. So that one CPE has to draw the power for this entire unit. So the low power aspect is very critical, right, because of the power. Now what happens is once, of course, the subscriber is going to be upset if he knows he's powering the whole neighborhood, right? So once the second CPE comes on, the third one comes on, you need to have an algorithm to share the power. So this is an interesting application that we're seeing of PON. And this is my favorite. So this is a GPON on a stick. So you can actually just put the PON menu and the optics, and you can see this. So why is this nice? So in a typical enterprise network or a DSLAM network, you have a WAN uplink, and then you've got the rest of the enterprise network. Right? This one is saying that take that SFP that you have, which is only optics, and you replace it with the stick, and suddenly you've got a WAN that's PON-based, and the rest of your infrastructure just remains the same. You don't really have to do anything. Seeing a lot of interest on this kind of a device coming out of AT&T and Orange, and I think this will become popular as deployments move from a copper-based one to a fiber-based one. This is a good intermediate step to actually start that. Okay. Questions?
Is it safe to say that basically the EPON is mainly used in China and Japan, whereas the GPON is more for European countries and then also India and so on?
Yeah, so it's an interesting question. So EPON was in islands. It started in Japan.
Right.
Then China picked it up with the China Telecom,
right,
and then had some growth in Korea and Taiwan. What happened in China, though, was interesting. And I did not think it would really happen that way, because China Telecom spent a lot of time defining their own EPON standard. Right?
Yeah.
GPON, they said, use the ITU. But suddenly, somewhere in the middle, the market in China changed from an MDU to fiber to the home. And the operators had to choose between a 1-1 into the home with EPON and a 2.5-1 with GPON.
Yeah,
And now it's changed. So China is almost 70% GPON now.
I see, I see.
But Japan's still EPON and Taiwan is, and Korea is still EPON.
Yeah,
But then when you go to the 10 gig now, it's again the whole game has started. So China is now doing a lot of 10 gig EPON because they're replacing their EPON with 10 gig EPON.
yeah, yeah.
What we've done is we've basically taken the guesswork out of the system. Our chips have multi-PONs on it, so
Yeah.
we have both GPON and EPON on the same chip, and then on the 10 gig we have all the PON variants on the same chip. So you basically can.
Yeah. Now, another question is that a lot of the providers now use the fiber to the curb. In that case, if you want to use the, in fact, even the dual chip that you have for EPON and GPON, when it comes to the curb, and then from there it's going to basically go to different houses and so on. Where would the power for that curb then come in? I mean, the device on the curb comes from?
Yeah, so that's an interesting question. So typically right now, the way it's done is there is actually, there's a battery in there.
I see.
You know, and it has a certain, it's got an AC connection if there's an AC, or it has to be reverse power.
Yeah,
right?
so somehow they should get it from the power company
Right,
in that
right.
area. Then I see.
So in the middle days, we talk about lining a little bit of copper on the fiber so they could run the 20 milliamperes.
I see,
Right.
I see.
But all of this is now, so you made a statement that a lot of the carriers are fiber to the curb. It's not the case. I mean, it's almost, I'm amazed how quickly, once they go to the fiber mode, it's all fiber to the home.
I see. Because
China is like 90% fiber to the home.
yeah, because Verizon, in fact, was in that fiber to the home business for a long time. But then, when you look at AT&T and then Comcast, they are mainly to the somehow to the curb, and then
Yeah. So I think they're also second guessing that one. Like, and seeing AT&T talking about an integrated home gateway.
Right.
Comcast talking about an integrated home gateway.
Yeah.
Google talking about an integrated home gateway. So I think it's going to change.
Okay.
Because it just solves that whole electrical question.
Right. Exactly. Exactly. Any other question? So at this time, let me thank Dr. Dighe for his very interesting talk. And then now there is the pizza. Please, start, using it. And then here it is. So thanks again.
Thank you.